We are continuing with the concept of logic minimization and utilization of Boolean algebra and Carnot map. Let's do some examples here. This is a circuit. This is a minimal realization of this circuit. And I have, let's see, I have A bar, B, D bar, which is this lower one. Okay, A bar, B, D bar, which is this lower one. Okay, this one. Then I have A, C bar. Okay, A, C bar. Which is this? This is A, C bar. This one is A bar, B, D bar. A bar, B, D bar. And then the other one is CD. Okay. CD is this one. Okay. So this is CD. This is A bar C. And the other one is A, B, D bar. Not even looking at the circuit, I can tell that I have 1, 2, 3, 4 hazards. Okay? These are the 4 hazards. This one is a hazard. The upper one is a hazard because between two adjacent ones, 0, 1, 0, 0, 0, 1, 0, 0, and 1, 1, 0, 0, there is no map. It's empty. Okay? And therefore this causes this hazard. I'm not looking at the timings or anything. All I'm saying is this is definitely a hazard. Okay? I have a gap here as well between 1101, 1101, this one, and 1101, and the one below 1111. And therefore this is, let me show you the gap, is this. This is the gap causing this. I have another gap here. I have another gap here. 1001 to 1011. And I have another gap here. Okay, 0111. This one. 0111, 0110. These are my 4 potential hazards. Do they happen? I don't know. And if they happen, what direction do they happen? I don't know. How can I tell? By looking at the delays. Okay, so let's look at each one of them. I'm going to look at 0111. 0111 changing to 0110. Okay? This is changing D from 1 to 0 or 0 to 1. So let's look at these two gates. D in the upper path is 8, in the lower path is 12. If D changes from the upper path, which is D1, to D1 to D0, which is the blue path, you get a glitch. When does that happen? It happens when D changes from 1 to 0, 8 nanoseconds after that, and 12 minus 8, 4 nanoseconds will be the duration of the glitch. Okay? So these are potential hazards. Of these potential hazards, you have to take each one individually and come up with the logical hazards, if there are any. And then the logical hazards give you these three information. First of all, D changes from 1 to 0. Then, how long after D changes the glitch begins, and what's the duration of the glitch. Okay? But then, the duration is 4 nanoseconds. It turns out that this duration is less than the output gate's delay, and therefore this duration doesn't happen. And therefore it is a potential hazard. It is a logical hazard, but it's not an electrical hazard because the little 4 nanosecond delay gets absorbed in the 5 nanosecond at the gate output. So it is not an electrical hazard. Let's look at this one. This one is 0, 1, this one. Okay, so we are considering this. Okay. Okay, what is this? A is changing from 0 to 1 or 1 to 0. A1 has this upper path, again 8 nanoseconds. A0 has this lower path, 12 nanoseconds. When you change from a path from with the smaller delay to a larger delay, you get a hazard, and therefore you have A from the smaller delay is 1, okay, to 0. The smaller delay is 8, changing from 1 to 0. The larger delay is 12, which is the 0 path. Okay, this is the 0 path. And therefore you get, when you change from 1, 1, 0, 0 to 0, 1, 0, 0, 8 nanoseconds after that change, your glitch starts, and then you have 4 nanoseconds delay. This again is not a logical hazard because it is a logical hazard, but it's not an electrical hazard because 4 is less than 5. Okay, let's look at the let's look at another situation. This one is we are considering this and this, these two here. These two, the C is changing. Okay, the C is changing. The longer delay path is 8 nanoseconds, is 10 nanoseconds, which is for C bar. The shorter delay path is 8 nanoseconds for C. Okay, and therefore when you change from the shorter to longer, that means ABC this direction or ABC this direction. Okay, or C changes from 1 to 0, you get a hazard, and then the duration of the hazard is 10 minus 8, and then that again is not an electrical hazard because it gets absorbed in the output delay. When does that happen? That happens, the glitch starts happening after the shorter delay, and the duration of the glitch is the longer minus the shorter. Okay? It is logical, no electrical. All right, before we close, let's look at ways of removing hazards. See, removing hazards is this. You're not going to look at the delays. You're not going to look at the output gate timing or anything like that. You say, well, I don't really know if the hazard is going to occur or not, but let's prevent it before going into the details, more details of the circuit. So all you do is you look at the circuit, you find that, okay, these four or these two and these two are adjacent, but no map between them. So put a map there. Okay, that becomes A, D. Okay, corresponding to this. What else? I have these two that again are adjacent and not covered. And therefore, I'm going to put another one here that covers only these two. Okay, which is A bar, B, C. Then you look up here, and then you see again two ones here that are adjacent but not covered. And therefore you put a third map here that becomes B, C bar, D bar. So you're really going against what you've been doing so far, which is logic optimization. But then if you're optimizing the circuit, also you want to prevent hazards, this is how you deal with it. Okay? What it means is I'm going to add a gate, B, C bar, D bar, a gate, AD, and a gate, A bar, B, C. You add these three gates, and then you are done with the hazard. So you don't really have to analyze anything because no hazard is going to occur anyway. What it really is happening is, remember we said that the output of the OR, one AND gate is dropping it before the other AND gate starts holding it. Okay, but in this case, we add a third gate that when these two are exchanging, one is going from 0 to 1, one is going from 1 to 0. When these two are exchanging, the third gate says, well, I'm going to hold the output to 1 while you two are deciding what happens next. So let me also do that original circuit we did. This is A, this is B, this is B bar, and this is C. Okay, this was an OR gate. Okay, this was the Carnot map. A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, C, 0, 1. Okay, what I have is the upper gate is this, A, B. The lower gate is B bar C, which is this. And where is my hazard? The hazard is where I have two adjacent ones that are not mapped, which is these two here. How do I fix it? A, C fixes it. A, C fixes it. Okay. All right, we are done with logic optimization, and we have looked at Boolean algebra, Carnot maps, Donkers, max terms, and finally utilization of Carnot maps in time.